Okay, so in the last video, if you haven't seen that yet, watch it first. We talked about how to calculate cubic foot per minute of flow on a flow bench. Technically, it applies to any pipe that's on a horizontal plane with no change in elevation with a known temperature and ambient pressure. So today's 30.13 ambient pressure in inches of mercury. It's 48 degrees in this room. I've already programmed that into the software. I want to show everybody the new Orifice. So if you look, all I did was interrupt the flow with an Orifice plate. There's a pressure tap on each side of the Orifice plate. Going to the Test 0510i digital differential pressure manometer. Set this back up where you can see everything. All right, so what we're gonna do is I'm going to do a test on this intake manifold, which you didn't see last time. This is the intake manifold that my blower mounts on. So it's basically an open plenum, very similar to a single plane in that respect. So I'm gonna start at 650 thousandths lift and work my way down. There's a couple reasons why I start high and go low. It's just good practice. If you're in a small confined space, the temperature in the room could change, and you want to do your high lift values first and work your way down. Honestly, everybody has their own way. That's just the way I like to do it. We're going to test at 28 inches of water, and we'll do correction factors if needed, and I'm going to walk through this flow test with you. I'm just going to do 650 thousandths lift. Now, with the blower manifold, I'm going to show you the way the blower mounts on here. It creates a sharp edge. Airflow does not like to go around a sharp edge. If I were to test this just like this, I would get an artificial flow reading. It would be lower than what it actually will be. And that's because the blower is going to mount flush with this sharp edge, okay? When it mounts flush, flow is going to have a little bit better turn. It's still going to have a sharp edge, which is going to reduce flow. That's inherent to this design. You cannot change that. However, what I can do, and what you can do at home, is when you do this, and this is just a cheap cardboard box. But anyway, when I flow test this, I'm going to wait until I get the flow steady. All right, and what this is going to do is act like a wall, okay? And that wall is going to simulate the blower being on there. Now, it's not perfect, but it's a lot better than flow testing it just like this, okay? So we're going to flow test this. And what I have here is the lift, the differential pressure across the orifice, the test pressure in inches of water, correction factor if required, and CFM. Okay? The software. Do not worry about CFM and feet per minute. That's wrong. This is assuming I'm using a pitot tube, which I am not. All we care about is this differential pressure, which is in inches of water across the orifice. Okay? If I were to use the pitot tube, this would give me an exact CFM readout without doing any calculations. But since we switched to the differential pressure measurement across an orifice, we just want to know this, and then we're going to do the math just like I did in the last video. So if you haven't seen that video and want to know how that works or what we're talking about today, watch that video and it'll make a lot more sense. Now, all right. I'm going to put this at 650 thousandths lift. Zero my gauge out here. So for one full sweep is 1/1000th of an inch. 2, 3, 4, 5, 650. Now, depending on the camshaft you're using, in a later video I'm going to talk about camshaft selection. You only really need to test with the max lift of your cam. Okay, the max lift of your cam at that flow number is all you care about. Any flow past that is not usable flow anyway. So my cam that I've spec'd out for old red after the new change is going to roughly roll into the 600 thousandths lift. I'm going to test at 650 just so I can see if there's any gain in adding a little bit more to it. And I'm going to do one test at 650 thousandths lift, and then we'll see what the math looks like. Okay. Hearing protection. Oh, this is going to get loud. So you may want to turn down your speakers because this will get loud. Okay, so if you notice, if you couldn't hear me, I put it up at 29 inches of water, okay? And I did that because if you notice, sorry, the reason I had to jump back over there is I had a breaker trip, and so I had to go reset the breaker on one of the motors. But anyway, when I installed this on here, you notice it dropped from 29 inches to about 28.2, something in there, 28.2. Now this angle may make it look higher, but that's because you're not looking level with the water. But 28.2 is close enough for the purposes of this video. But anyway, that's just to show that almost 1 full inch of water difference by using this. That's a significant amount of flow, okay? Now, we were at 28 inches of water, so I'm gonna use that as my test pressure. All right, I'm gonna bring the camera over here and we're gonna do the math, okay? Just like we did it on the last video, okay? So, if you look, we had 4.48 differential pressure, okay? So it's 4.48. Now there's no correction factor, so I'm just going to use a multiplication of 1. If the inches of water was a little different, we could put a correction factor in there, okay? The cubic foot per minute, we're going to calculate just like we did on this in the last video, okay? So you're going to do the square root of the differential pressure, 4.48, okay, divided by the calibration of my orifice, which is 9.01 inches of water. If you don't know what I'm talking about here, look at the last video. The orifice plate that I'm using flows 375.56 inches or CFM at 9.01 inches of water. So we're taking the differential pressure, 4.48 divided by 9.01. We're going to multiply that by the known flow at the calibration scale, 375.56. And that gives me 200, I don't know why it's focusing, but 264.82 CFM. Okay, so 264.82. 264.82 CFM with the manifold. Now, the flow test is going to look the same all the way down. So for the purposes of the length of the video, I'm not going to go through a whole flow test. That's the process. You get to your lift value, leak check your bench before you start flowing. I did that before the video. If you want to know how to do that, I can describe that over, or I can do a video on it if enough people ask. But make sure you leak check. Once you're done with your leak check, make sure you calibrate your Orifice plate. Make sure nothing has changed, that it hasn't shifted, you don't have any new issues with it, which there shouldn't be. Make sure your hose is connected to the intake side. If I was blowing through the exhaust, I would move it from up there to down here. And in the last video, we talked about well type manometers. This is a Dwyer well type manometer. It's the same exact one used on an SF600 bench. Okay, the only difference is the SF600 bench has one that goes up to 40 something or 50 inches of water. This one goes to 36. Okay, and that's the Dwyer name. This uses the red gauge oil with a specific gravity that's different than regular water. It's 0.82 something. And the significance of that, if you were to measure this 1 inch of water, it would be more like 1.1 inches, okay, physical. So because the red gauge oil has a specific gravity less than 1, then the scale's gonna have to stretch to compensate for the difference in how far it travels. But anyway, so that's a vertical manometer, a well type, okay? If you're doing this at home and you're on a super tight budget and you don't want to buy one of these, then you can use regular hose, okay? Get you a 2x4, okay? And you're just going to stretch this thing out and make sure it goes up to at least 20 inches on each side, okay? Each side, put your 0 in the middle, and then look at the last video where I showed the scale above and below that middle portion, okay? And and the differential pressure is going to be your total inches of water. All right. So that's a YouTube manometer. This is the well type manometer. This is a little bit more expensive. You can find them online for sale. People have them. All right, so the next thing I want to talk about is net flow versus gross flow. Just like a paycheck. You get a paycheck, it's a gross amount of money, and then after taxes and all that, you have your net paycheck that you're going to get at home, your bring home pay. Same thing with here. When you flow cylinder heads, okay, cylinder heads have a certain flow figure. These heads flow 285 CFM roughly at 650 thousandths lift. When you put the manifold on, you see it flows 265 roughly CFM. So it's about a 20 CFM loss at the peak lift value. Okay, it's not the same losses at every lift, but at peak lift, it loses a lot, and it's that sharp turn that you see. When you're playing with clay, okay, and you put clay on the end of the cylinder head, okay, it has a very smooth transition for that airflow to go around. On your manifold, it has a sharp turn. Now, this is still not completely net flow, because to get a full correct net flow, the blower would have to be on it, and the throttle body on top of that, or carburetor. Because it's not practical for me to put a 50-pound blower on top of that, because of the flow bench, I can't really do that. But if you're doing this at home, and you build you a bench and you're using a carburetor and a regular dual plane, single plane manifold, put your manifold on there, put your carburetor on there, make sure it's clamped nice and tight on the back, and there you go. That is your net flow. Okay, net flow is where Superflow on their SF600 bench, that's where that formula, that your CFM times 0.26 times 8, which is your number of cylinders, that formula that they're using is pretty accurate if you use two things: your net flow for one, and you don't use your peak flow. You use the average flow, okay? And this also depends on camshaft, and I intend to do a video on that. I've already wrote down some thoughts of what I want to talk about when it comes to that. But a lot of people look at their peak flow number and they're like, okay, that peak flow times 0.26 times 8, even if it was net flow, they're like, oh man, my 300 CFM is good for 620 horsepower. That's just not true, okay? You need to know what your average flow is, and this is why mid-lift flow is overlooked a lot, and mid-lift flow is the most important and what will dictate power, okay? If you have two cylinder heads, one flows 300 CFM and the other flows 265 CFM, okay? You're gonna think this 300 CFM head is gonna be faster or make more power than the other. And it just depends on the average flow. If this one flows 200 CFM at 300 thousandths lift, 220 CFM, and then it just jumps up because you just made the port really, really big to flow good up top, then that thing's gonna be a dog down low. And that one that flows 240 CFM at 300, 250 and 260 CFM at 5 and 600 lift, that average flow is going to be higher. And that average flow across the full sweep of your camshaft is gonna make more power than the one that flows really low down low, and then all of a sudden it picks up a ton of flow up top, okay? So that's really important to understand, and more in detail than I'm going to go in on this video. I just wanted to show you a flow test and then the calculation, and you saw how easy that was, okay? And that's going to get you your CFM, okay? Now, since I've calibrated that tool to this bench and that manometer, it's very accurate, okay? This thing flows 265 CFM in this setup on an SF600 bench. On mine, it's 264.62. Within 1 CFM, I think is really good. So just make sure you do all the calibrations correct. Make sure you leak check. Leak check's very key. Make sure it's sitting on the bore plate correctly like it would be on the engine. And that's it. So that's it for this video. On the next video, I'll go into more detail of cylinder head selection, camshaft selection for your application, okay? The stages of camshaft and stages of cylinder heads, and it's just ridiculous. That is complete nonsense, and that makes me chuckle a little bit. You need the cylinder head and camshaft for your engine, your combination, okay? What do you intend to do with the truck, with the car, with whatever you're doing? Are you going to be off-roading? Are you going to be racing? Is it going to be a street strip, basically just a street car that you like to take to the strip, okay? Street strip is not, I have a street car that is a race car. No, you have a street car that you take to the racetrack, okay? Drag cars, race cars are purpose-built for the exact RPM that they intend to make power, and it's not the same as a street car. You take a drag car that's purpose-built for the drag strip and you put it on the street, your Honda Civic is likely to beat it from red light to red light. It's just because of the setup. This truck I built, specifically designed the camshaft and the ports and the manifold porting that I've done is very specific to the street that I'm using it on. Okay, the amount of boost I intend to push in it is, like I said on the last video, just adds additional oxygen, okay? So it's very important to develop for the best flow at the right volume, okay? That is where people also mess up is how many cc's in that intake port do you want? Well, if you put a 235 cc intake runner on a 350 small block, it's going to be a dog on the street because you're not going to have any airspeed to make that low end torque. Okay, inside the port, your low lift numbers are going to be terrible. And there's a lot of tips and tricks I can help people with as far as port development. And if you want to see just a little sneak peek of what I'm talking about, when I was developing the cylinder heads that I have, let's see here, if I can find the page. That's what I started with. That was mapping out the cross-sectional area in every part of the port. Okay. And this is what I ended up with. Okay. Now this is specific to my engine combination. Okay. This is not going to be for yours. You may have a different setup. So it wouldn't do me any good to sit here and describe why I chose specific measurements for different parts of the port, because in reality it needs to be set up for your application. So that's it for this video. If you want to see more, let me know. Subscribe. I'll put some more videos on as I come up with stuff, and I will be doing one on camshaft and cylinder head selection, and how to derive horsepower potential from head flow. Okay. It's an exact science. It's not just 0.26 times 8 and that's what you get. There's some more into it. Camshaft, lobe, angle, lobe deflection, those kind of things all matter, and what RPM you can expect out of a cylinder head or a combination, okay, given your average flow numbers. And what RPM am I going to make peak horsepower? What RPM is it going to make peak torque, and what is my horsepower potential? All that can be derived pretty close, and I'll show you how to do that. That's it. Okay, so I went ahead and finished the flow test. And if y'all see, you can see the depressions there. Those are the differential pressures from 200 to 650 thousandths lift. Now, one thing I wanted to show you, okay, you see this right here, 29.5 inches of water. I couldn't get it down to 28. My bleed valve is too small. And then when I dropped it to 3 motors, I could only get it up to 27.4. Okay, so this is where your correction factors come in. Okay, now I talked about correction factors in the last video, but I wanted to go ahead and show you how you do this. So your correction factor is the inches of water you want the test flow at, and this is what you actually are at. Okay, 0.974244, whatever. Okay, that'll be your correction factor. You can round that to 4 decimal places and it'll get you really close. So over here, I'm gonna put my correction factor as 0.9742. Okay, now 27.4 inches of water. 27.4 inches of water. It's going to give me a multiplier. Since it's less than my test pressure, I'm going to get a higher. It's going to be more than 1. I talked about that in the last video. 1.0109. 1.0109. Okay, round to 4 decimal places, get you close enough. Okay, so the way this is going to work, okay, is when we do the square root of the differential pressure, we'll do 200 thousandths lift. Divide by 9.01. Just remember, this is not the number you would use in your calculation. This is the differential pressure on my specific orifice that's calibrated to. Okay. multiplied by my calibrated 375.56 at 9.01 inches of water. That means at 200 thousandths lift, I'm at 144 now. This is where your correction factor comes in, okay? My correction factor was 1.0109, so you also multiply by your correction factor, okay? Now you only do this if your test pressure is not the one that you intended to do. 1.0109. So it's actually 145. Okay, and I'm just going to round to the greatest whole number, okay, because 0.2 of a CFM is not going to matter, so 146 CFM, okay, you can see that there. Alright, so the next one, just do one more example, okay. This is going to be 300 thousandths lift was 2.98, okay, and then the correction factor was higher than 28 inches of water, so the multiplier is actually less than 1.9742. So 210 CFM, okay, at 300 thousandths lift, okay, and I'm just going to keep going down the list. This is real quick, 3.9, okay, I have no correction factor because I was at 28 inches of water, so 247. Okay, the next one was 4.24 inches of water differential pressure, and that was at 500 thousandths lift, and that's 257. Okay, and I can actually round that to 258. Okay, now 600 thousandths lift is 4.34. 260. You can see that the air is starting to slow down. It's starting to get what you call port stall, okay? This is where the port is not going to flow any more air hardly. And if we raise it from 6 to 650, we get 4.48, which is 264. I'll just round that to 265 because it's 0.8, 0.2 CFM is not going to matter. All right, so this is what my setup flows. Okay, I'm sharing this information with you. Okay, for some reason people think this is like a kept secret. Okay, now if you notice as I get closer and closer, if my camshaft only goes to 500 thousandths lift, if you look, I'm not gaining a lot here, okay? I'm not gaining a lot of flow. So if I lift that cam all the way up to 650 thousandths lift, I'm not going to gain much horsepower, okay? So let's just assume, okay? Let's just assume that this is perfectly net flow, okay? We're going to go 265 minus 258. That's 7 CFM I'm picking up with a whole 1.5 thousandths additional lift, okay? 7 CFM, okay? Now, that's 7 CFM times, let's just use Superflow's formula, okay? Now, I have some mixed emotions with this, but what, 14 horsepower at the crank. So at the wheels, you'll be less than that. Is that worth the drivetrain, or let me say the valve train instability that you may have? I don't know. If you're looking for every 1/10 of a second and you're on a race car, yeah. If you're on a street car and you want reliability and low maintenance, if you were to lift this to 500 thousandths lift, you'd be fine, okay? Now, the camshaft going in old red is a solid roller, okay? And that solid roller is going to have about gross lift just right at 600 thousandths lift, with the 20 thousandths hot lash that I'll be putting in it. 20 thousandths hot lash because it's a very aggressive solid roller lobe design. It's going to give me some room in case I put better heads on it that flow better, or I put a different manifold on it that gives me better net flow. characteristics. But again, I'm not going to gain a lot of power from 500 to 600 thousandths lift. We're talking, you know, a few CFM, okay, even less, because I'm not lifting to 650 thousandths. So I just wanted to show you the how to do your correction factors now. If you are building a DIY flow bench like this, and your flow bench only flows 10 inches of water, you can do this correction factor and get your flow at 28 inches. Is it going to be perfect? No, it's not. And that's because airflow dynamics slightly change as you increase the test pressure. So the characteristics down at low test pressure are not going to be exactly the same. So is it a perfect science? No, but it'll get you pretty close. If you want to have real good solid numbers and you want to compare your head to other heads that your buddies are doing, importing, you need to be able to flow 28 inches of water just to make sure you know that your numbers are correct. Okay? All right, that's it.